We'll discuss about what is a process. In olden days systems, there will be only one program to be executed in the computer. The program had a complete control of the system, and since it is only one program, and it had access to all the system's resources. Nowadays, in current days, the computer systems allow multiple programs to be loaded into memory and executed concurrently. The evaluation required the firm control over more compartmentalization of the various programs because the several programs concurrently are started executing, then we need a strict mechanism to safeguard each program in the main memory. And a process is nothing but a program in execution. A process is the unit of work in a modern time sharing system, a unit of time in a modern day system. Now, a system therefore consists of a collection of processes, operating system processes executing system code and user processes executing user code. Potentially, all these processes can execute concurrently. That means operating system processes and user processes. The second thing is switching the CPU between these processes. The operating system can make the computer the more productive and powerful. Let us see a small example. Even on a single user system like Microsoft Windows, a user may be able to run several programs at one time: a word processor, a browser, and an email package. These are all using by the user. When if the user can execute only one program at a time, the operating system may need to support its own internal programmed activities such as memory management. In many respects, all these activities are similar. So we can call all these activities are called as processes in the later stage. What is actually a process? Now we'll see actually the process is the program residing in secondary memory is an executable file. If that executable file loaded into the main memory using program counter shows the next instruction to be executed. When it starts execution, then it's called process. A process executes, as a process executes, it changes its state. The state of a process is defined in part by the current activity of a particular process. Each process may be in one of the following states, that is new state, running state, waiting state, ready state, terminated. New state means the process is being created. Running process instructions are being executed. Right now this process is executed by the CPU. Waiting, the process is waiting for some event to occur. And fourth one, ready, the process is waiting to be assigned to a process. It needs a CPU time, so it's waiting to get the CPU. Terminated, as a process completes its job, the process has or process when finished execution is called as a process termination. These are the following states of a particular process. The process may comes in any one. Process may lie in any one of these states. These 5 states. If it is created, it's a new state. If it is currently right now executing, running. Suppose while running particular process, it needs some IO operation. Then it's waiting for the IO operation. Then it goes to the waiting state. And after IO operation is completed, that process again ready to be executed by the CPU. Then it will be in a ready state. After completion, it will become terminating state. This is the diagram of process state. If you see, this is a new process is created. Then as soon as a new process is created, it will enter into the ready state. From the ready state, this scheduler brings the process to the running. Running means right now CPU is running or executing these processes. While running, any interrupt happens or operating system trap executed or operating system any interrupt happen, then it will send back to the ready queue. Again from the ready queue, it is loaded into the running state. If particular when a process is in running and it's want some input output events to occur, then it will go to the waiting state. Waiting to occur input output activity. After the completion of the input output activity, that particular process again enter into the ready state. From the ready state, it is going to be loaded into for the execution. After completion of this process, the process is terminated. This is a diagram of a process state. Now we'll discuss about the process control block. Each process is represented in the operating system by a process control block. So PCB, process control block, represent each and every process. Suppose there are 4 processes, means then 4 blocks of PCBs we need to maintain. What is this job of process control block? It stores all the information of a particular process. Process state, program counter of a particular process, and the CPU registers this process data, and which registers are affected in the CPU, that data, CPU scheduling information, memory management information, accounting, IO status information. All these informations are stored in PCB. Each PCB is allocated for each process. Now in detail, we will discuss what is this process state. Process state may be new state, even we have seen in the previous diagram. Process may be in ready state, process may be in a running state, a waiting state, halted, and so on. These are the states of a process. What is the job of program counter? Program counter always points to the next instruction to be executed of that particular process. Okay, my dear friends. Next we'll see what is CPU register. The CPU registers are index registers, accumulator, stack pointer, general purpose registers, and any condition code information, program counter. And one thing here, all these registers, CPU registers and program counter, this data should be stored before any interrupt occurs. As soon as interrupt service completed, to resume the previous operation, we need to store the content of program counter and CPU registers. Next, CPU scheduling algorithms. The process are also about, suppose there are 4 processes are loaded in main memory. Then which process has to be selected and given to the CPU for execution? This will be carried out in a CPU scheduling algorithm. Next, memory management. The process or all processes are to be stored in main memory. So we'll discuss here about page table, each process size. If it is segment, we are dividing into segment or page size, page table. We'll discuss in memory management in detail. Next, what is this accounting information? This information includes the amount of CPU and the real time used. For each process, how much time a CPU used, and time limits and process numbers. All these information will maintain here in accounting information. And the last one, IO status information. This is IO devices, information regarding IO devices. Total number of open files. IO devices allocated to a particular process. How many IO devices are allocated to a particular process? How many are open? All these the data will be stored in a process control block. So it is like a repository, or any information of a particular process is going to available in this PCB block. Let us see this PCB block diagram here. What we discussed, we are shown in a graphical representation. Process state. Process state, every process has its number. Process state comes under either new state, running state, waiting state, halted, all this comes under process state. Process number comes under accounting information. Right now, what is the process number? We'll get from accounting information. Program counter. In this process, in this particular process, what is the next instruction to be executed? These are the registers. We discussed about the registers like accumulators, index registers, stack pointers, general purpose registers. Memory limits. What is the base register and the limit register, and page tables, segment tables? All these will be stored here in memory limits. A processor, while executing the process, it should give it is where it is located. That gives from in the base register gives from which part onwards in the main memory this particular process has to be executed. Limit register gives from the base register how many or offset it is, how many bytes, what is the length from the base register, how many bytes of code has to be executed. That length will be given into the limit register. Next, list of open files, IO status information. This is IO status information, gives list of all the open devices, open files, how many input output devices are needed for a particular process. This information it will maintain in list of open files or IO status information. Let us discuss this CPU switch from process to process. It is also called as a context switching. Now in this diagram there are two processes are available, process P0 and P1. These two processes to be handled by the operating system. Now in previous slide we already discussed about process control block. The job of the process control block is to store all the information of a particular process. Since here there are two processes are available, we need to maintain two process control blocks. So we see here PCB0 and PCB1. Now let us see. Before, suppose a process P0 is executing, suddenly while executing it got interrupted via system call. It got interrupted. Then right now the process while executing, its present status is stored in a particular PCB. Suppose P0 is executing, its data should be stored in PCB0. So before interrupted, all these process data should be stored in PCB. After resuming, after coming back from the interrupt, this present PCB0 data, by using this, the process starts execution from where it left previously. And let's see this diagram. In this diagram, process P0 is started execution. From the beginning it started. In the middle, it is interrupted or system call. Then all this data of a process P0 is saved in PCB0. Next, process P1 wants to execute. Whenever P1 want to execute, that since previously P1 data is stored in PCB1, the PCB1 process control block of 1 to be again reloaded to that particular process, then it starts execution. Whenever again interrupt occurs for process 1, that should be stored again in PCB1. Save the status into PCB1. And this continues. This is the continuous like this. And again P0 want to execute. Reload the state of PCB0 into the process P0. Let's discuss about process scheduling queues. As process enter the system, they are first put into the job queue, which consists of all processes in the system. Whatever the processes, all are comes into the system. The processes that are residing in main memory and are ready and waiting to execute are kept in ready queue. These ready queues are generally stored as linked list. We'll see what is this device queues. For example, whenever a process needs an IO device, that IO device may be used by several processes in the particular system. So whenever this process want that IO devices, but the IO devices is busy, is engaged with some other process, so this IO device, this process should wait for this IO device in a device queue. Okay. Next, this processes migration between the various queues. Suppose a job queue, all the processes are in job queue. From job queue, it go to the ready queue to the device queue. After device queue is completed, it will again come to the ready queue. So this will continue until the process completes its job, terminates, until it terminates. As soon as this terminates process, then PCB process control block is also deallocated. Until then, process should be in any one of these queues. This diagram shows the ready queue and the various IO devices queue. This ready queue maintains a linked list, and header indicates pointers to the first and final PCBs in the list. Process control block PCB means. Each PCB includes a pointer field that points to the next PCB in the ready queue. This depicts the ready queue and IO devices queues implemented using linked list. So linked list always have a header and tail, and this one node links to the other node. Okay. This diagram is representation of process scheduling, as we discussed right now. All the processes first in job queue are ready to be executed by the CPU. While executing time, a particular process, while it is in executing state in the CPU, it may go to any one of the state. Maybe it needs IO request, then it will need to go to the IO queue. If that particular process time is expired, then it is time slice expired, then it will come back here. If a process needs a child process to be executed, then until its completion is execution, it will be in the this fork and child queue. If any interrupt occurs, then it will be in wait for interrupt queue. These squares are all queues. Okay. Now these circles will do the particular operation. A process continues this cycle. Ready queue, CPU, again any one of these queues. From these queues will go to ready queue. This process will continue this circle. Then when this cycle breaks is either CPU should completely execute this particular process, so that that process will go to the termination state. As soon as a particular process is terminated, it PCB process process control block is deallocated. So all these data will not be available in the particular process data in the process control block. We'll discuss about schedulers. Why we need schedulers? There are multiple processes are on to be executed, but space to execute all these processes are very less. So we need to store all these processes into a secondary memory. From the secondary memory, the processes are stored and they are ready to execute. From the secondary memory to bringing a particular process to the main memory is called long-term scheduler. Next, short-term scheduler or CPU scheduler. Processes are all now loaded by long-term scheduler into the main memory. Now his main memory is filled with the number of processes. The CPU scheduler selects any one of the process and gives for execution to the CPU. This is called short-term processor. In long-term scheduler, it executes much less frequently. Minutes may separate the creation of one new process and the next. The long-term scheduler controls the degree of multi-programming. The long-term scheduler may need to be called only when a process leaves the system. Because of the long interval between executions, the long-term scheduler can afford to take more time to decide which process should be selected for execution. Next, let us discuss short-term scheduler. It is executes frequently. The short-term scheduler must select a new process from the CPU frequently. Process may execute for only a few milliseconds before waiting for an IO request. Very often, the short-term scheduler executes at least once every 100 milliseconds. This is called medium-term scheduling in the diagram which you are seeing on the screen. Before this, we'll discuss about. In general, most processes can be described either IO bound or CPU bounded. What is this IO bounded process and the CPU bounded process? Let us discuss briefly. In IO bounded process, in that most of the time spends with doing IO operations instead of computation. A CPU bound process, in contrast, generates IO requests infrequently, using more of time by doing computations. By doing more computations is called CPU bounded process. Doing more IO operations is called IO bound process. It is very important that the long-term scheduler, what is the job of the long-term scheduler? It selects a process in the secondary memory and places into the main memory. The job of the long-term scheduler select a good process mix which should consist of IO bound processes and as well as CPU bound processes. If this mix is not good to be done by the long-term scheduler, then system will become imbalanced. Suppose the long-term scheduler loads all the IO bounded processes into the main memory. Then ready queue is always empty. All processes are in waiting for the IO devices. So there is no job for CPU scheduler. For example, if long-term scheduler loads all the processes of CPU bound processes, then all the IO devices, access devices and IO queues are empty. This will make system imbalance. So system with the best performance should have the combination of CPU bound and IO bound processes. Okay. Some operating systems such as time sharing system may introduce an additional intermediary level of scheduling. Not only long term scheduling, one more scheduling algorithm, that is medium term scheduler, what we are seeing on this diagram. The key important idea behind a medium term scheduler is sometimes it can be advantageous to remove processes from main memory to reduce the degree of multiprogramming. It is overburdened, then we'll remove some of the process, and after that the process can be reintroduced into the memory and its execution can be continued where it is left. This is removing is called from the CPU when it is multi-program is increased to reduce the multi-programming. We remove some of the processes from the CPU is called swap out. So that half executed, partially executed are kept here in this here, and after some time this will be given to the ready queue. This is called swapping and will be started execution. After execution, the process is terminated.